This is the screencast for section 4.3, example 1. We're going to look at the first derivative test. The first derivative test will tell us where the original function f is increasing and decreasing and therefore has a maximum or a minimum, because where the original function is increasing and then changes to decreasing, f prime is going to change from positive to negative, as you know from chapters 2 and 3, and then therefore f will have a local max. Opposite for when f prime changes from negative to positive, there will be a local min on f. F prime does not change signs, then there is no extrema. Now the places that we can test for those extrema to occur are called critical points. A point on the interior of f where the derivative is 0 or does not exist is called a critical point. So let's look at an example. Example 1, for each of the following functions, use the first derivative test to find the local extreme values and identify any absolute extrema. Alright, so I need to find the first derivative. So f prime is 3x squared minus 12. Okay, just need to find the zeros or places where x values where this would be undefined. And that would be at 2 and negative 2. So now I'm going to test on a number line. Very important to label this number line as f prime because that's the function we are testing. I'm going to test where negative 2 and 2, they both make f prime 0. But let's see what happens to any number to the left of negative 2. So for example, like negative 5. I get a negative times a negative, which will be a positive. In between negative 2 and 0, or negative 2 and 2, the easiest number to test would be 0. If I plug 0 into f prime, I get a, let's see, 3 times a negative times a positive. So overall that would be a negative. And then any number after 2, say a billion, I would get 2 positives. So overall would be positive. Therefore, I can tell you that f would be increasing, decreasing, and then increasing again. See, if the slopes of the derivative are positive, that means f was increasing. And then if the slopes of the derivative were negative, that would be decreasing. So f is kind of taking on the shape of, let's see, increase, decrease, increase, sort of. Which means I have a maximum here at negative 2 and a local minimum at positive 2. So I wrote out my conclusions and my justification. F has a local max at x equals negative 2 because f prime, its derivative, changes from positive to negative, which means f, the original function again, changes from increasing to decreasing. So that critical point, negative 2, right here, resulted in a maximum of f because f prime changed from positive to negative, which means f changed from increasing to decreasing. Now f has a local min at the other critical point, x equals 2, because f prime, its derivative, changed from negative to positive, which means f changed from decreasing to increasing. Now, I'm sure you can already see it's very, very critical, that you label which function you are talking about. What does f do versus what does f prime do? F does not change from positive to negative. That's above or below the x-axis. F prime does. F changes from increasing to decreasing. So you have to be sure that you are clear as to which function is doing which. Now as for the second part of the question, identify any absolute extrema, well, this f of x here is a third degree polynomial with opposite end behaviors, so there are no absolute extrema. Now before we go on to the other example, I skipped over a couple of pages of notes that now that we've done one, I want to show you what they mean. This page right here, this is the second page of your notes, shows a diagram of what's happening. So in f is changing from increasing to decreasing, so f prime would be positive to negative, changing from positive to negative at this critical point. F prime itself is changing from positive to negative, above the x-axis to below the x-axis. Now we also have an f, a local maximum, even though it looks a little funky and maybe is not differentiable there at c. So that would be a critical value where the function is undefined, where f prime is undefined. That's still okay. F prime can change from positive to negative, still creating a local max. And we have the same circumstances for a local min. Now we do have some situations for no extrema, where at that critical value, although the derivative may equal 0, the function is increasing before and after it, creating no extrema, or decreasing before and after it, creating no extrema in f. A situation that we won't see in this example or now try problem is a maximum at an endpoint or a minimum at an endpoint. Let's say they cut off your domain at a and b. If your function f is decreasing after a left endpoint, there was a local max there at f. So if f prime is negative after a left endpoint, f had a maximum. Or vice versa, if there was a if the function is increasing before a right endpoint, that right endpoint had a maximum. So the derivative would be positive before the right endpoint. And the same is for minimums as a left endpoint or a right endpoint. Now as we continue on to part B of our example 1, we're going to take the derivative of g and do the first derivative test to find, again, any local extrema values and any absolute extrema. Now I needed to use the product rule, and the derivative of e to the x is e to the x. I have that common factor in each term, so I'm going to factor that out. And now the inside of the parentheses is a polynomial that I can factor and find all the critical values after I set g prime equal to 0. E to the x doesn't give us any critical values. There's nowhere where e to the x is going to be 0 or undefined, but it will play a part in whether our result is positive or negative. My two critical values of g prime are -3 and +1, which means g is going to be, let's see, increasing, decreasing, increasing. Now it's probably not going to look exactly like this because it's not a polynomial. But this is what it's doing, which is at the critical value -3, creating a maximum, at the critical value 1, creating a minimum of g. Now sometimes you will be asked to explain why in words, but as for right now, since you've labeled this number line as g prime, you've showed where it's positive, negative, and positive, and then you've made your conclusion, this number line is your justification for why g has a local max at the critical value x equals -3 or a local min at the critical value x equals 1. Now this function is bounded below, and I know that from pre-calculus because I have a e to the x being multiplied by a polynomial, so that e to the x is going to kind of shape the graph. Don't believe me? You can graph it. Since this is bounded below, the minimum there is the absolute minimum, x equals 1. In the now try problem number 3, we're going to use the first derivative test to determine the local extreme values of the function and identify any absolute extrema, and of course we will support our answers graphically at the end. So first, I have to use the first derivative test to find the local extrema, so I need to find the first derivative. Now I'm going to set that equal to 0 and find the critical values. And I find that the critical values of y are -1, 0, and 1. So I'm going to label on my number line y prime, because that's the function I'm testing. Put the critical values of y down on the number line and test each interval. And I got negative, positive, negative, positive, which means the graph of y is going to, let's see, decrease, increase, decrease, increase, which makes sense. It's a fourth degree polynomial. Its end behaviors should both be facing up because the leading coefficient is positive. So I'm going to say that y has a local max at its critical value x equals 0, and it has local mins at x equals -1 and 1. Now the directions do say identify any absolute extrema. Well, let's see. Definitely not going to have an absolute maximum, but I might have an absolute minimum, so I need to plug in f of -1 and f of 1. And I get that both of those critical values result in the same y value of f. So they are actually both absolute mins of y. And of course you would type y into your calculator and find the minimum, maximum, and minimum to make sure that you have done this correctly and to support your answer graphically.